Alrighty, so today, if I could have your attention, today we're going to look at what we call debugging. You've probably sort of heard that expression before. Generally, when you write code, it never works perfect the first time, and to fix it is usually called debugging. Okay? Now, there's actually a story behind the word bug, and I think we can trust Wikipedia on this one because we know there's lots of computer science nerds out there making sure that this kind of stuff is correct. So, use of the term bug to describe inexplicable defects has been part of engineering jargon for many decades and predates computers and computer software. There is a common story that's usually told that in the very first computer that had vacuum tubes and actual electronics in there, there was literally a bug, like an actual insect in there that was causing the problems. The word bug is actually way before that. Thomas Edison wrote the following words in a letter to an associate in 1878. It has been just so in all of my inventions. The first step is an intuition and comes with a burst. Then difficulties arise, this thing gives out, and then the bugs, as such little faults and difficulties are called, show themselves in months of intense watching, studying, labor, a requisite before commercial success or failure is certainly reached. Baffle Ball, the first mechanical pinball game, was advertised as being free of bugs in 1931. Problems with military gear during World War II were referred to as bugs or glitches, and so on. So it's not just a computer science term. That myth about a bug, I don't know if it's actually true or not. While it is certain that the Harvard Mark II operators, that's one of the first computers, did not coin the term bug, it has been suggested that the incident contributed to the widespread use and acceptance of the term within the computer software lexicon, which means vocabulary. The related term debug also appears to predate its usage in computing. The Oxford English Dictionary's etymology of the word contains an attestation from 1945 in the context of aircraft engines, so not just a computer science thing. Okay? In software development projects, a mistake or fault can be introduced at any stage during development. Bugs are a consequence of the nature of human factors in the programming task. They arise from oversights or mutual misunderstandings made by a software team during specification, design, coding, data entry, and documentation. For example, on the very first Mars rover project almost 10 years ago, there was a bunch of Europeans working on part of the system, and there was a bunch of Americans working on the system. They forgot to tell the Europeans that all the specifications were in feet and pounds. The Europeans were using the metric system. $10 billion later, they had a really expensive crash on Mars. That's a bug. Nathan had a little less costly bug this morning, didn't you? Yes. But bugs are everywhere. All right. So how can we debug? Let's learn about debugging. Okay. So Liberty Basic actually has a debugger feature, which I really wish Scratch would have. Liberty Basic comes with the debugger feature. Type in the following simple code for x equals 1 to 100, print x, next x. Please do not put 100,000, Connor and friends who put in big numbers yesterday. So please type for x equals 1 to 100, print x, next x, and then I'm going to show you how the little bug icon works. Go. Once you've got it in and you've run it, you'll clearly see that it prints from 1 to 1,000, and you'll notice that it takes a few seconds. At one time, you actually used loops like this to slow down the code so that it would sort of wait. There was like a pause kind of feature. We don't use that anymore because it burns up a lot of processing power kind of thing. If you want to debug this, I would like you to click on the little ladybug button right there. Okay? And you'll see that it opens up the run window, and it sort of opens up a window as well here. You'll notice that it says x equals 0, and it's highlighting this line. It's manually going through step by step for you. Okay? Now there's step into, there's step over, and there's step out, and I don't really understand what those do, and then there's the animate one, which goes real fast. The one I use is the step into. So if you just click like this, you can see it doing what? It's going through the code, and it's showing you what it's doing, which line it's at. And you'll notice that it's also doing what to the x? It's bumping it up. It allows you to see inside the brain, inside the variables of the code, to see what's going on. This is pretty useless right now. We know what it's going to do. There's no problem here. But it allows you to figure out what those variables are. Okay? Nathan, can I talk about your little error this morning? Is that okay? Okay, so Nathan had a little error this morning. He had, I'm just going to see if I can duplicate it here. He had something like this. Card 1 equals int of rnd of 1 times 13 plus 1. Have I got that right? Okay. Will it run? Yes, good. Okay. Now, Nathan made just a tiny little typo. It was no big deal, really. What he meant to do was do this, but what he did was he did that, Alex. And he said to me, Mr. Bennett, every time I run it, the numbers are always the same. 1 and 1. 1 and 1. And 1 and 1. And always the same. Like always. I might have a mistake in my thing here as well. Oh. No, I've got 1, 2. Oh, it should be like this, shouldn't it? Should it?
No, there's a times after R&D.
There's one that's fine.
Oh, that's the one there. Thank you, Con. I had an inadvertent bug, one that I didn't mean to create. Now let's see what happens. There we go, 11 and 11. They're always the same. Okay, he didn't spot that, but when you run the debugger, you would see that card 1 and card 2 are both 0, and as we go through it, oh hey, I got 7 and 6. Why did it print 7 and 7? There, now you would see it. So you would see that the variables are 7 and 6. Why is it not printing correctly? Oh, I see. I got the wrong thing there. Okay? So that's an easy fix to fix. The debugger works really well because it allows you to see what's going on inside the code. Okay? Now there is a debugger help feature as well, although I think a lot of that is disabled on your computers. It has to link to online. I can show you the link to get here. I'll put it on Schoology, but there is help as well for that. Okay? All right, so I would like you to, here's your practice assignment. Type in the following code, use the debugger, and perform what we call a variable trace. A variable trace means you write down, yes I know, shocking, on a piece of paper, you write down what the variables are equal to as the program runs. Okay, so here's the code that I want you to write in. Okay, I'll let you get it in there, and then I'll show you how to do the variable trace. What you were to do is to type it in. We're going to run the debugger, and we're going to perform what we call a variable trace of the variables. Okay, so you've got it in. I guess, do I have it in yet? I guess while I was waiting now, I should have done that myself, eh? Would have made sense. Good thing I have the ability of copy and paste. Okay, so let's just run it and make sure that it works. You probably tried that already. Okay, so it does the counter and it does the square. Now, the first thing I noticed right away, do we really want it to go counter, square, 2, 4, counter, do we want it to go counter, square every time, Alex?
What?
Do we want this to be showing the word counter and square every time? Or do we want that like at the top and then just show the numbers? Probably just like that, right? So what should I do? This print right here should be where? Right there, before the 4, right? Okay, so let's move that so that it's outside the loop. And now let's run it again. That looks better, right?
Yeah.
Right? So you guys should make that change, Nathan. Are you watching, Lance? What change did we just make, Lance? So where did I put it? I put it before the for loop, not before the print. It is the print. Print counter square. It's before the for loop, right? So that it's not looped over and over again. All right, I'm now going to show you a variable trace. On the first Liberty Basic test, question number 7 says, perform a variable trace. 6 of you will not know what that question refers to because you're not listening right now. If you're one of those people, put your hand up. You're not listening right now. Excellent. Okay? Here's what a variable trace looks like. You run the debugger like this, and you write down on a piece of paper all of the different variables that we are using. So in this case here, we have variables max value, and we have x, and they are currently equal to 0. So you actually write that down on a piece of paper, and then you step through it. Okay, we input, I'm going to use, let's go 8, so it's a little less. Now, when you run the debugger, when you press enter, nothing happens because it doesn't know to go to the next step. Christian, you need to watch. I don't know what you're doing, but I know you're not watching. You have to actually click through to tell it to go to the next step. Why did it jump down to here? Why did it not go into here? Because max value isn't bigger than 20, exactly. What's my value of max value? 8. Cross out the 0, you put in an 8. What's the new value of max value? 8. X is still 0. I keep going. X now becomes 1. I do this. This is called a variable trace. Okay? It's a way to find out where your mistakes are. Okay? This is a pretty useless little one, but I'm just showing you what happens. The 8, will the 8 ever change? And the X simply does what? It's just going to go 2, 3, 4, and so on. You really should do it as you go along. There's no mistake here, so we're not going to find anything. Right? But that's what a variable trace is. You write down all the variables, and then you hand write down exactly what those values are. Okay? That is a variable trace. Okay. It says here, use test values of 5 and 21. I should have did that. I used 8. Okay. Practice number 2. Type in the following program and run a variable trace. This time there is an error in here. There is an error in here. Okay? You're going to have to see if you can find it. If you find it before you run the debugger, that's fine. You might in the typing part. See if you can find the error in there by using the debugger. All right. Now, if I run the debugger, Alex spotted it right away. If I run it in Liberty, let's just close this one off here. So I've got it typed in here. You should be able to spot it using the debugger because you'll notice you've got num and number, right? And as you go through, what number would you like to see multiples of? I'll say 7. You have to hit enter, and then remember you have to go into here and you have to keep stepping through. You'll notice that it stops right away. How come? Because it goes for x equals 1 to num. What's num? 0. Okay? It's another way of spotting those little typo errors. Okay? Now, I made it quite obvious. You might have done something like this. You might have had num, it's spelled like that. Or, yeah, it's French, right? I know it's not. You might have that. Okay? Those are the kind of things that you can spot by using the debugger. Okay. I think I'm done yakking at you for a while. Here's hand-in number 6. Now, I actually made a sheet for you as well. This one is probably one of the more challenging hand-ins. So if you have earbuds, you're trying to sneak a little listen, or you're not paying attention, you should stop and you should really, really, really listen carefully. Okay. How many people know what a factorial is from math class? Nobody? Yes? Dakota, what's a factorial? You know? You remember? You don't remember? Okay, I will show you. It's not hard, but you do have to be listening to get this. Okay, so the assignment is, put your phone away, Alex. You need to be listening right now so that I don't have to explain this later. Listen. The number one rule for learning is listening. Pay attention. Convert the sum of numbers program from lesson 5. So you should have saved your hand-in program from lesson 5. convert it to find the factorial of a number. Factorial means to multiply all integers below that value together rather than add them. So rather than going 4 plus 3 plus 2 plus 1, like we did in the sum of numbers, you have to multiply 4 times 3 times 2 times 1. Okay, Dakota? Multiply. Don't start yet. Listen. It'll be a whole lot easier if you listen for the whole explanation. Okay, the symbol for factorial is the exclamation mark. It doesn't mean yell the number. You don't just go, 4! Math joke. Bad math joke. Then, we're going to use the step minus 1 feature to count backwards again. If the value of the factorial becomes bigger than 3,000, then it should stop the message program with a too big message. It's not too big for the computer, it's just going to take forever. Connor. Okay, so we're going to limit the factorial value to be 3,000, Lance. Are you listening? Excellent. You should need the use of the debugger to complete this program. There is a common error that every single person usually makes. Okay? So really use that debugger. I need you to, I want you to hand in pseudocode on a piece of paper. Hand in pseudocode on a piece of paper. The code will be done normally, and a variable trace on paper. For the test values of 5 and 8, I must get a variable trace on paper. Have I made myself clear? You not only hand in the computer part, you hand in on paper a variable trace along with your plan. Okay? Here is the sum of numbers program if you haven't completed it yet. The one thing you do need to do is you need to change the variable sum to the variable fact. Okay, so you're going to go like this. You're going to go fact equals fact, and instead of plus count, you're going to multiply. This whole greater than 10 thing, I don't think is true. You do have to check to see if the factorial is bigger than 3,000. I won't do that part for you. Okay? You are going to need the use of the debugger. This is what it should look like, Travis. I need you to watch so you know what it's going to look like. Don't start now. Listen for the full assignment. And watch. Close your lid. I can see you're distracted by something. This is what it should look like. What number would you like to calculate factorial for? Because there's a question mark, that implies we're going to use a what, Lance? Input. The 6 is inputted. Okay, and then it's going to print 6 exclamation equals. And Christian needs to watch. Close your lid there, Christian, so you can pay attention. You're going to print 6 exclamation equals. Then it's going to say calculating. And then on the next line, it's going to go 6 times 5 times 4 times 3 times 2 times 1. You may or may not be able to figure out how to get rid of this last star. That's a little bit of a bonus one. And there's the answer. 6 factorial is equal to 720. How come? Because 6 times 5 is 30, times 4 is 120, times 3 is 360, times 2 is 720, times 1 is 720. It's not bigger than 3,000, so we print it. If it is bigger than 3,000, like if you type in 15, it should say calculating, and then it should say 15 times 14 times 13. Notice that it goes all the way down, but it says too big. How come? Because it's way bigger than 3,000. Okay? You've got all of that information on that sheet of paper. You see it there? Okay? This will take you a while. You'll likely get some time tomorrow as well. Good luck.